Well, I can lean back in the chair all the way now. The ice is gone. In fact, it's a very, very lovely day and it's quite warm. This recording is being made at New Year's Eve. It's the last day of 2020, and this class is for the 2021 semester class, Theoretical Physics. And this is Class A. We'll do a little bit of review for you, the Taylor Series expansion, and matrices. You've probably seen matrices and know all about matrices, but we'll take a little time to review. It's the first week of the semester. And then we'll do groups. And groups are interesting, very powerful in physics. And I remember in undergraduate school not learning groups in any of my physics courses, but I took a philosophy course with a professor that was a particle physicist, and he was shocked when we didn't know what groups were. He asked the class and on the spot taught us in a philosophy course what a group is. So I hope you enjoy that. So this is our first class in terms of the letters. Now, we did have a class, I called it Zero, which was introductory physics to fill everybody in on some basic concepts from physics in case you didn't take introductory physics class. And this is the first letter of our class A as we run through A through Z. So hope you enjoy the class today, and let's get started. Chapter A, Taylor Series. A rotation, matrix, and groups. Little group theory. We will start here with A1, the Taylor series, and this will be a review for you. We're still in the first week of class here. There's Brooke Taylor. And the Taylor series is very, very important. We consider a function f of x and express it as a power series, a constant plus another constant times x to the first power, second constant, x squared, and so on, say a to the n, x to the n, on off to infinity. And we want to match this function. So you want to like do sculpting, like think of yourself as a sculptor, that this is like marble and you want to sculpt these coefficients so that you get a function. And the way to do that is put in 0 for the function, and that'll just pull off the a naught. So you pick a naught to be whatever the function is at 0. Then what you do is you take a derivative, and if you take a derivative of the function, then this first constant piece is 0. You get an a1, and then you get 2 a2 x squared plus 3. Originally, you would have a3 x cubed, say. But when you take the derivative, you pull 2 down from the x squared one, get this, then you pull the 3 down, then you wind up with the x squared. And then this is n, an, x, n minus 1. So if you put in 0 for this derivative, you're going to get just the a1 piece. And then if you take the second derivative, then you'll have 2a2 by itself plus 3 times 2. We'll put the times 1 in there. And that's going to be x a3 times x. And then here, you'll have here n and n minus 1, a to the n, x n minus 2. So when you put in the 0 for this one, so we'll go ahead and say here, put in x is equal to 0, because that's what that notation means. Then everything goes away, and you get 2 a 2. And then for the third derivative, which we can just put a little 3 here and put into 0, you'll have the 3 times 2 times the 1 will pop out. And that'll be the 3 factorial. So you can get the idea here. This is 2 factorial. And the fourth case would be 4 factorial. So your nth case will be n factorial, a to the n. And now you have the solution. You have the an's would be equal to, take the nth derivative, put in 0, and divide by n factorial, and that would give you the an. And then for the function, you can write it as a summation from n equals 0 to infinity, an x to the n. And if you want, you can just put this in for the an. Very, very important in physics. That's called, here's the notes, the Maclaurin series. When you expand, we say we expand about x equals 0. And in general, you could expand about some other place. Let's see, here's a, x minus a squared. And that would be the Taylor series in general. So the Taylor series, when you have expansion about the origin, that's the Maclaurin series. And it's very important to know these. I have practice problems here for you to look at. You don't turn those in. But here, it's nice to know a few of these by heart. And I encourage you to work on these. In other words, the cosine of x would be here, it would be a 1 minus x squared over 2 factorial would be the first terms, and then the sine of x would be x minus x cubed over 3 factorial, and then e to the x would be 1 plus x, and here if you had 1 plus x to the n, that would be 1 plus nx. You're looking at these when x is small. So when x is small, you can just keep like the first term or two. Sometimes you might just keep the first term, maybe 2 terms. And it's nice to have those by heart. Okay, we now go to A2, a use of Taylor expansion. And here's a quick little overview of physics. If we make a little plot here, really more like a set of like entries, where this is size and this is large and this is small. We're doing this in reverse so that the size, when you go to the right, gets smaller. And then here, if we have speed, we'll do it the regular way. This will be slow and this will be fast. So here are areas of physics. When you have large things, which means you can touch them. You can touch a baseball, it's large. You can touch the earth, it's large. And that's classical. That's classical mechanics. And you might associate here Newton. We can associate Newton here and put a date, say 1687. Here he worked on the Principia book. And then if you look at the fast regime, this is relativity. In other words, Newton's laws had to be modified. So this is relativistic mechanics. And we can think of here Einstein. And for a date, we can go with 1905, the special relativity. So really the guide here is the speed of light. In other words, that's how you know if it's fast or slow. So if the velocity, say, is a lot less, c is the speed of light, then you're in classical realm. Here, if you get really small, like the molecules, then you have quantum mechanics. And you can think of Schrödinger, Heisenberg, and we can go with a date of around 1925. Now up here, where you're fast, so you can think of it like 4 boxes. So up in here, you're in a realm that's fast and small, relativistic quantum mechanics. Now that's a very difficult area, and Dirac made the first breakthrough in 1928. I put a question mark here because work's still going on in this area. And you can think of here the constant is h, the Planck constant. That helps get a scale. This is like an energy times a characteristic time. And if your characteristic energy times time is really small, like near h, which is something like in the metric system, something like 10 to the minus 34th, energy joules times seconds, that would mean you're in the quantum realm. Otherwise, you're in this realm. So you can think of an example here of the Taylor series as doing a Taylor series expansion on a relativity equation, and you would recover the classical. Now, when we talk about theory in physics, it's important to understand that we do not mean hypothesis. We mean theory as you might use it in music theory. It's an accepted body of knowledge, harmony, laws. I mean, theory can mean hypothesis. Theory has like several definitions, but the one that's typically used is theory as a law, like you could say like music laws of music, or say electromagnetic theory, which some of you I think are taking now, electromagnetic theory with Professor Booker. So if you look at one of the equations, like in relativity, is a Lorentz contraction, that if you have a ruler that's moving by, then it'll shrink. Beta is the velocity over the speed of light, and this is going to be less than 1. So when you subtract something, from the 1, this will be contracted. So like if you think of here, you have a frame K prime that's moving and a frame K that's at rest, and the ruler is in the K prime frame. Then when you observe it from outside, like simultaneously, make a measurement from beginning to end, you get this contraction. And so this is not predicted by Newton. Like what is that? So here, and also the time, like if you have a watch here, this watch here, when you observe it, appears to be running slower. So this would be like dilation. Now we're going to look at these formulas later, but the point I want to make here is that if you look at one of these things, like here, 1 minus beta squared to the 1/2 power, the Taylor series expansion, this is 1 minus a half beta squared. So, if you have 1 plus something small to the nth power, that's going to be 1 plus n times something small. And this n, if it's like a fraction, still works. I remember asking my math calculus teacher in college if this formula that we did in the first class, a plus b to the nth power, and you had the Pascal triangle, like to work stuff out, would that apply if n is not natural, like a number 1, 2, 3, 4, 5, 6? And he said, yeah, still works. So see, it still works there. So what that means, if the beta is small, this is approximately 1, and that means there is no Lorentz contraction. there is no time dilation. There's absolute time, absolute space, and you recover Newton. So this is an example of how physics evolves. When a new physics theory comes out, or a new law, then when that law is more powerful, this law would contain Newton. But you would want to keep Newton, because if you're an engineer, you don't want to be using complicated equations when all these betas are going to be zero and they're going to simplify. So that's a nice example of what's called the correspondence principle, in a sense, where you can reduce from one realm an equation to a simpler equation. And so you can think of reduction this way from quantum mechanics, and here, reductions like that, say, or reduction like that. A3, matrices. Now, you may have learned about matrices in high school. We have here a 2x2. Let's do a 2x2. I will assume that you were sick that day in high school and missed it. So here's a matrix, and here's another matrix, a B matrix. And you can think of this as the first thing is like your row, A1, that's the row. And the second number is your column. 1 is column, second column. So B1, and the second number, 1 column, 2 column. So this is the second row, first column. Second row, second column. And then when you multiply these together, what you do, and you're going to get another 2x2, you take these two and turn them sideways and smack them against there. So that would mean A11 hits B11, and then A12 hits B21. Then when you do this next one, so you're really looking at here 4 entries, you would take this, turn it sideways on this thing, so that's A11, B12, A12, and that would be B22 down there. You would take this one and go sideways with that, A21, AB11, plus A22, B21, and finally the last would be this one with that one. A21, B12, plus A22, B22, all right? It's always good to work these things out and then check it with the book. Remember, my math teacher in high school, as a senior, said that you always should study math with a pencil in hand, like a pencil or a pen, and like be writing things out. So you can check that, that this is indeed what we have here, that we didn't make any mistakes, but we worked it out on our own. Sometimes you can write this like, say, row, column, or some may just go I, J. That's kind of cool. And then here, there's some shorthand notation to get the products, say C, I, K, would be to take an A, I, J, and a B, J, K. So let's just check one. Suppose I want to check 1 and 2. That would be up here. This is 1 and 2. Then the I would be 1, and the B here, the second thing would be a 2, because this is the first row, and this is the second column. All right. But then what you would do here for the second and the first, you would sum. You would let the J be 1 and then 2. So it'd be 1 and then let it be 2. And check. That's correct. Isn't that neat? So this is a shorthand notation. And Einstein used the convention that if 2 things appear, then it's understood that you're doing a summation. So J from, say, 1 to 2, I, J, B, J, K, and that's the matrix I, K. That's the product. It's a very elegant way to write the product of two matrices. Okay, now we're off to do 4. A4, the rotation matrix. This is very, very important in many areas of science and physics and engineering. We have here an x-axis and a y-axis, and we're going to rotate the axis. We have an x prime axis and a y prime axis. And some point here from the origin, and this point P can be expressed in terms of x and y, or x prime, y prime. And we'll say this angle is theta. So if we were to drop, say, perpendicular all the way down to the x-axis, this piece here would be your x. And coming down from, say, here down to the bottom, this would be y, this one here. However, you could drop down this way to the x prime axis and have an x prime. And you could also drop over here, to get a y prime. See, y prime, up there. This is a y prime here, y prime, and this would be x prime here, like that, x prime down there. And that's like having two languages. Say x might be English and the prime may be Spanish, and we're going to do a translation, a dictionary. Now it's important to note that I am rotating the axis, not this. You can think of this as like a vector. Pull an arrow there if you want. And some books like to rotate vectors. I'm not doing that. Rotate the axis. So your formula will be different with a minus sign if you rotate the vector down. That's like rotating the axis up. See, if I kept this axis the same and rotated that down, I'd have a similar effect. So just be aware of that when you look at other books. So what is x prime? Well, the secret in doing this, I discovered, if you make yourself a cute little rectangle here, like this, let me go out like that, let me go that down like this. This is the secret to understanding everything, this little rectangle. So these are all right angles here, all right angles. So now watch this. X prime, that would be this one here. This x prime here is equal to this x times the cosine of theta to get us that far. So it's x times the cosine of theta plus this extra piece here, which is this piece, which is y times the sine. See, this angle here is also theta. If you look at this angle down in here and say this is a right angle, the way you can see this is that these two are opposite, so they're the same. These are the same. And since that's a right angle, that's a right angle, you're basically, in this case, you want this right angle down in here. It's a little bit hard to keep drawing this stuff, that you want this right angle. So if you have this right angle down at the bottom, and then these two are the same, the third one had to be the same. That's a little bit tricky. So that is a right angle there, but we just didn't need that for the analysis I'm making here. So these two are the same, these two are the same, and then these have to be the same. So this here is the same. This is the little rectangle we drew. So it's the same as this length, which would be y times the sine of theta. Then for y prime, that would be this one here. This y prime can be thought of as being the bigger one, subtracting that little piece. So the bigger one here is y times the cosine of theta. And write this one second. Write the y second. And I'm going to subtract this little piece, which is this piece. Now we're going to have to go to this piece here, which is x times the sine of theta. So x sine of theta. And we have it. So y prime is a shorter segment here. So you take the big piece, which is y times the cosine of theta, that's here, and subtract the little piece, which is x times the sine of theta. And that's it. Now we can write this as a matrix operation. Watch this. If you write down cosine theta, sine theta, minus sine theta, cosine theta, x and y, the way this works, now that's a column vector. You take this sideways and smack it, and that's going to get you the x prime one. So if you take this sideways and smack it, you get x cosine of theta plus y sine of theta. And that's the x prime. That's this one. Then if you want the one down here, which is the y prime, you take this sideways and smack it. So it's minus x sine of theta plus y cosine of theta. And that is the other one. So it's very, very elegant. Then the rotation matrix can be defined as, you can use a little, it's arbitrary if you want to do matrices like that, or, do that symbol, doesn't really matter. So cosine of theta, sine of theta, minus sine of theta, cosine theta. And this is for rotating the axis. You rotate the axis, that's important. All right. So now let's go to A5 and show some superpower here. And that is trig identities. Now, trig identities can be nasty. For example, if you want to know what the cosine of alpha plus beta is, that's not trivial. But watch here. If you want alpha plus beta, that angle, what you can do is you can have the two matrices, and we could do a cosine of alpha, sine alpha, minus sine alpha, cosine alpha. And here, cosine beta, sine beta. And we're applying this matrix twice. All right, we're going to rotate twice. All right, sine beta, cosine beta. And if you wanted to put this one second, you could. It doesn't really matter. You can do it in any order here when you rotate. Like if you want to rotate like 70 degrees, you can rotate 30 first and then 40, or you can rotate 40 and then 30. But see, when you do this, this is going to be, a big matrix here is going to be, it's going to have here cosine of alpha plus beta, sine of alpha plus beta, and then minus sine of alpha plus beta, because this is the combined, like this is some theta here. So this is the one, let's say with the theta, and this would be cosine alpha plus beta. And then that means this has to be this one turned sideways with this. So that means the cosine of alpha plus beta is equal to the cosine of alpha times the cosine of beta, and then minus the sine of alpha, the sine of beta. This is amazing, because this is like a hard trig identity. Like, what is that? And like it's derived like in pretty much one line, all right? So that's awesome. And then if you want the sine, see here's the sine, you can get the sine of alpha plus beta. That would be up in here by taking this sideways with this. So that would be, if you did that, you would have the cosine of alpha, hit it with the sine of beta, and then plus the sine of alpha hit with cosine of beta. And you get the other one. Then you could play games like letting beta become minus beta, and use the fact that cosine's even function, and the sine is an odd function, and get all kinds of stuff. So this is an example of the magic of theoretical physics, all right? And tricks in mathematics, all right? So that's very good. Now, A6 is a challenge to visualization of the trig identity. And I have a nice picture in the book for this. So this is one where you can just focus. This is a visualization. So with visualization, we stare. We stare at pictures. So to visualize this, what we're saying is that, and this is, I'm going to let you do pretty much this on your own to just visualize this. I have here a rotation here of beta, but then I have in this alpha, I'm showing the alpha angle to get to the 1. This is 1 unit. And I'm showing you using the formulas that we derive with the cute little box. I'm showing you here how you can visualize the pieces of this particular case where you have alpha minus beta. So this is for you to stare at on your own, all right, as a little exercise, a little challenge to do visualization. Notice that you can also find something that's totally crazy, and that's the cosine of alpha plus beta plus gamma. You can figure that out by just sticking another matrix on there with the gamma, and it's not that hard to multiply them out. You don't have to multiply all of them out, just the one to get the cosine and the other one to get the sine, and you can get then incredibly difficult. This is reminiscent of Feynman, where he would know how to do calculations that would be so short cuts in there that might take someone else like 6 months to do something, and he would do it in one night and do the more general case. So that's cool to look at that. So, challenge yourself to see if you can visualize. And, that visualization, everyone's different in how fast things take. So you take your time and you look at that picture in here and you see if you can visualize all these pieces at your own pace. Notice you can get the tangent ones in here. These are the practice problems that you can work out. And look at the power. This is the style of theoretical physics, to derive things in elegant ways. We move now to A7, groups. I remember once having a teacher in college who was a particle physicist, and he said, "Y'all, you know about groups?" And we were all like in his class, like, in fact, it was a philosophy class I think he was teaching. And we said no, and he was like shocked. So on the spot, he told us groups. So, I don't know how popular groups are in undergraduate education, because I never really had groups covered until grad school. So let's do groups. So groups, first of all, we can consider a set. A set is a set of elements. And for a set of elements, you could have, say, a person, you could have a box, you could have pi, you could have 1.3, we can have a house, we can have the sun, all right? Set of elements. Now a group is a set of elements with certain properties. So you're not gonna be able to have something like that mixture. So here you have A, B, C, D, ... where a binary operation is defined. And for the binary operation, we're going to use the little dot symbol like this. And that would mean, for example, A dot B is defined to be something. Like it's going to mean something, all right? A dot B. So you really can't imagine like having a person and all these. You can't have an operation there, but with numbers you can. Like you'd say take, like if these are, say, regular counting numbers, you could say take 3 and take 4 and like add them together. You see, that's a binary operation. Then you get like 3 plus 4 is 7. So here, A is an element of the group. That's a symbol there. It means it's an element of the group. That means A is in there. So you have to have these properties now. Now these are properties. The first property is closure. Closure means that for A, an element of the group, and B, an element of the group, that means that if you take the A and B and do the binary operation, that's also in the group. That'll be in the group also. Second is association. That means if you take A with the binary operation with B, and you do that first, and then do C, that's the same as doing the second two first, and then the first one. I was fascinated with this because I was fascinated why commutation wasn't in there, and that's interesting. Commutation's more strict, it turns out. And I thought, wait a minute, commutation is like 3 times 4, 4 times 3. You know, it's like, isn't that simpler than like taking 3 things? But not really. So commutation is not included in the definition of the group. So it may work or it may not work. And that's, if it does, then we say it's an abelian group. All right, and we'll get to that in a second. So we skip commutation, which is what you may have learned early in your education next, before association. Then there is identity element. There's an identity element. Okay, so there's closure, association, identity element. I exist in the group, and such that A, when it's working with the I, with the binary operation, you get A back, get the same thing back. You might think of like if you were multiplying numbers, like 1 would be the identity, like 1 times 2 is 2, 1 times 3 is 3. And then 4, inverse element, and here I'll put a little -1 superscript. It has to be in G also, such that A, when you do the binary operation with the inverse, you get the identity element. And the group is abelian if A with B is B with A. So that's the commutation. So if commutation holds, so that's not a requirement for the group. That's like an additional, if it happens to be there, then you have a more specialized group with the commutation working. That's the abelian group. Now, you want to be very careful here. Like mathematicians have taught us to be mathematicians, mathematicians have taught us to be very careful. Suppose you operate with the identity on the other side. Would that equal, because technically this is a right identity. The identity is being used on the right side. What about the left side? Now, you gotta be careful. So you want to think like a mathematician, very, very precise. So how we can prove this is the way I like to prove trig identities in high school. You just play around, like start with the answer and work, and just to try to get the other answer and then work backwards. So I'm going to start with what I'm trying to prove. So if A, I'm going to start with this. Then what I'm going to do is I'm going to apply on the right hand side. I'm going to take this thing and apply it with A inverse. So just whatever this is, you take it with the A inverse. So that A inverse. Then this is I. And I can do these in any order. So I could do these first, because association, so that's I. And then identity with identity is identity. So I could now start here and go backwards to prove this. So this is kind of cool. It shows that the identity can be on the left. All right, that's nice. And for a practice problem, why don't you show that you can have the inverse working on the left-hand side, and you get the identity also. And the last section, A8, the military group. This is a fascinating discussion that I found published in a magazine, a sophisticated magazine, military group and the square root of -1. And here is the reference. It's a magazine called Quantum. It's a very, very advanced kind of magazine, but written for youngsters, but with deep, deep things. And this article that was in their marching orders talked about the group. And that's what I'm going to do now. Basically tell you what that article had to say. So we make ourselves a group where we have in the group the elements attention, about face, left face, and right face. So A means attention. Maintain the direction you're facing. B, about face, means you're going to turn around. L, left face, means you're going to face to your left. Right face means you're going to turn to your right. That's the military group. Now, we want to check closure. So when you check closure, you make a multiplication table. A, B, L. And what we're doing here is going to do all the possibilities. So suppose you do attention and then attention again. Well, you're going to be attention. You're not going to be changing anything. You're going to be still facing the same way. Suppose you do attention and then about face. Well, that's the same as doing about face. That's the equivalent of doing about face. Suppose you did attention and then left face. That's the equivalent of doing left face. Suppose you did attention and the binary operation with right face, you'd be doing a right face. Now, if you come down here, same thing. If you go about face and then attention, that's still about face. Left face and attention would still be left face, and right face and attention still be right face. So far, we have closure. Suppose you did about face and about face. Well, that would be like back to where you are. That's like doing an attention. Suppose you did an about face and then a left face. All right, well, if you were facing this way and then an about face, you'd be here. And then you could do left face. Left face would be down here. So about face and then a left face would be the same as doing a right face. What about an about face and a right face? An about face and then a right face would be like doing a left face, you see? We just said do it again. About face and then a right would be like doing a left. Suppose you did a left and then an about. Well, if you did a left, we just go ahead and do these. If you do a left and then an about, it's like doing a right. If you did a left and a left, left, that's doing about. If you did a left and then a right, you'd be coming right back. That's an attention. If you did a right and then an about, it'd be like doing a left. And if you did a right and a left, that would bring you back. And if you did right, that would be about. So that is the multiplication table, and we have closure. We have demonstrated closure. That's amazing work there. But now comes the bonus, comes a surprise. And that brings us to the concept of isomorphism. Isomorphism, there's two groups that have the same multiplication table. They're said to be isomorphic. So what I'm going to do here is I'm going to look at another situation where I'm going to put here in this group, I'm going to have the number +1, -1, the imaginary number I, and -I. Now, you can make a plot of these things. If you have 1 here, -1 is back there, and then here, this would be I, and this would be -I, like the imaginary axis. But let's say that we don't know this. We don't know that. But we can make a multiplication table because you know how to multiply. So now we're going to check the group with the 1, -1, I, and -I. 1, -1, I, and -I. And we're going to find the multiplication table for this case. 1 times 1, 1 times -1, 1 times I, 1 times -I. Coming down this way is easy. 1 times 1, we have that one. One of these, one of those, and one of those. -1 times -1 is a +1. -1 times I is a -I. -1 times -I is a +I. I times -1, -I. I times I, -1. I times -I is a +1. -I times is going to be I. And then -I times I would be a +1. And then -I would be a -1. Okay, now let's look at this. A, B, L, and R. So A is 1. So here's A. Here's another one. A, and A. B is your -1. So here is a B, and here's a B, and here's a B, and there's a B. And then R, or let's do L next. L is your I. There's an I, there's an I, there's an I, and there's an I. And then R is a -I. There's an R there, an R there, and an R there, and an R there. Isomorphism. So in other words, A is like the 1, about face is like the multiplying by -1, and then left face multiplying by I, which means if we did not know this, and we're racking our brains out in high school like I did to try to place where is I along this line, it's not there, it's imaginary. This isomorphism says you know what I is. It's a left face. Well, left face means 90 degrees up here. And -I would be a right face. So what this is showing us is that we understand deeply what multiplying by the square root of -1 means. It means rotating left. It's a left face. It comes from the isomorphism. Beautiful. And then, of course, we know there's a complex plane and we can graph these things that way. But trying to put us back when we were in high school, we didn't know this. The group would teach us that multiplying by I is leaving the real axis by 90-degree rotation to the left up here, and then it's where your I is. And then if you multiply by I again, you get -1. You're down there. And multiply by I again, you're down there. See? And go around and around and around. And here for a practice problem, this is fun. They had these on the SATs, like what's I to the 100th power, or I to the 101 power minus I. And if you think of the I as a left face and a minus I as a right face, when you do 4 left faces, if you do 4 left faces here, 1, 2, 3, 4, you're back to where you started. So that secret is like if you have 100, then that's 25 groups of 4. So if you did 25 groups of 4, then you're going to come back to like the 1. So, and then here's like 1 extra one, has to be an I. So you can do these quite quickly. All right, that's our first Class A for our course.